Hi, my name is Seth Adams. This is Physics 2211, Lab 3, Black Hole. All right. This lab has two parts. Part one is to analyze the motion of a star to determine the mass of a black hole. Part two is to use the calculated mass of the black hole to determine the initial velocity of a spaceship to get close enough to the black hole without crashing and it still being able to leave the system. This lab demonstrates the effects of Newton's second law and its relationship with momentum. A little preview at our results from this lab. The mass of the black hole was calculated at 9.58 times 10 to the 33rd kilograms. The F net force of this was 7.66539 times 10 to the 28 newtons. The F net of the parallel force was 1.05024 times 10 to the 28 newtons. The F net perpendicular force was 7.5873 times 10 to the 28 newtons. And for part two of the experiment, we got the initial velocity of the spaceship being negative 4.85 times 10 to the 7th, 2.5 times 10 to the 6th, 0 meters a second. The fundamental principles of this lab are Newton's second law, which is the momentum principle. And momentum is the mass of an object times its velocity, so that the change in movement is m times the final velocity minus the initial velocity. In this formula here, delta P equals m Vf minus Vi. We can find that using the velocity update formula, which is Vf equals Vi plus F net over m times delta T, and the position update formula, which is final position equals initial position plus the average velocity times delta T. Another part of these fundamental principles is the parallel and perpendicular components of the net force, which is the gravitational force. The parallel component, called p hat, is parallel to the direction of motion. The positive p hat direction is pointed to the direction of motion. Direction tells us if the object is speeding up or slowing down, and it has to do with the change in the speed of that object, what the direction of p hat is. The perpendicular component, which is n hat, is perpendicular to the direction of motion. The positive n hat direction is pointed to at the center of the orbit, and it has to do with a change in the direction of the orbit. These formulas down here are the p hat and n hat formulas. The universal gravitational force is the only force exerted on the system in both parts of the lab, and that's because they're both in space. This force is an attractive force between two objects. The variables that are defined in this equation are g, which is the gravitational constant of 6.67 times 10 to the 11th, m1, which is the mass of the black hole, object 1, m2 is the mass of the planet in part 1 and the mass of the spaceship in part 2. R hat is the distance between the two objects, and it's the magnitude of the vector. All right, for the coding. In the coding, we use the momentum principle, the parallel perpendicular components, and the gravitational force to find the mass of the black hole. The initial conditions are over here in the corner, right here. And for the results of experiment 1, the system was the planet, the surroundings were the black hole. The mass of the black hole was 9.58 times 10 to the 33rd kilograms. And multiple masses were given during each iteration of the model. It could be a possible source of error here because of rounding values at each iteration, because I found this value by taking an average of all the calculated black hole masses. The net force in its components calculated F net equals 7.66539 times 10 to the 28 Newton. F net of the parallel force 1.05024 times 10 to the 28 newtons. F net of the perpendicular force is 7.5873 times 10 to the 28 newtons. The coding for part 2 of the experiment focused on the gravitational force and the velocity and position update formula. Here are the initial conditions of this experiment down here in the corner. And in the code, you can see right here is the mass of the black hole on the planet. the force of that, and right here, the velocity and position update formula are being used. The results of part 2. The system for this one is the spaceship, the surroundings is the planet, and the black hole. The initial velocity of the spaceship is negative 4.85 times 10 to the 7th, 2.5 e to the 6th, 0. Velocity when leaving the planet, and although it comes close to the black hole, it is able to leave the orbit and not hit either the black hole or the planet. The x component is in the negative direction due to the beginning position of the orbit. The spaceship shoots off of the planet to the left. The initial velocity moves much higher speed to the left than to the right. This allows it to overcome the gravitational force between the black hole and the spaceship. What if and what does it mean? What does it mean? How is the net force and its parallel and perpendicular components different from the rate of change of momentum and its parallel and perpendicular components? In this experiment, they are not different and they end up being set equal to each other. What if? What initial velocity would your spaceship need to have in order to enter some kind of orbit around the black hole? The initial velocity that would be required for that is negative 5 times 10 to the 6th, 2.5 times 10 to the 6th, 0. This right here is the y component doubled, but in the negative x direction. This means it has a much lower speed when it exits the system. This leads to the planet having a circular orbit, while the spaceship is much more elliptical, like this picture I have down here at the bottom. That's it for Lab 3. Thank you for watching.